Hello again and welcome to another tutorial. In this tutorial, we are going to be modeling an electromagnet in CST Studio. So now some things to have in mind during this is how does the electromagnet look like? How are the fields distributed? What are the corresponding Maxwell's equation? Are the H and B field vector or scalar fields? What is the relationship between the H and the B field? And what happens with the H and the B field are continuities. So these are some questions that you should be able to answer going through this tutorial. Now to model the geometry. Now the dimensions in previous examples we've been pretty much given the dimensions as input, but now we have to kind of get it ourselves from the image given here. So first of all, I think it should know it's not here. So first of all, open CST Studio as usual and select low frequency as a problem type, and then in the home tab, which is this, click on okay, sorry about that. In the home tab, click on setup solver and select M static solver. So if you should go to this, then you click on setup solver and select magnetostatic solver. That's the M static solver. And in order to simplify the implementation, change the length to cm. So remember that we have our units here, and clicking on it, change it to cm and leave the frequency in hertz. Now create a new material with relative permeability of 1000. So you go to materials, you right click on it, so right click and new material, then the permeability is 1000. And okay, I could also change the color to match, so I'll change it to red to match the diagram. So we have it as material 1. Now in the modeling tab, click on the brick and create the lower part of the electromagnets. Create 3 bricks, and then we use the boolean. So we refer to the first image. Now this is the central axis, so we'll take all our measurements, all our distances from this 0 point. So we go to modeling because we want to model our geometry, and go to brick. And when you click on brick, you see this red dot, you just click on escape. Now I want to model this lower part of the block. Now you see that the dimensions from the height of this is 8 centimeter, so that means this is 4 and then the bottom part should be 4. So from this point to this point, if you can see it, from this point to this point should be 2 cm, and then you have 2 cm to complete 4 cm. So for y, we have that we call this the maximum point, and then this is the minimum point. So the maximum point would be -2 from the axis. So we go to here and -2, and then the maximum point is -2, and then the minimum point is -4. Then for the x-axis, we have that the total length of this is 10 cm, and then it's centralized. So we have -5 on this side and then +5 on this side. So for your x, we have -5 and +5. Then for your z is 2 centimeters. Now it's 2 centimeters, but then centralized. So we would have -1 and 1, which would give a total length of 2 centimeters. So, and then make sure that this is material 1, which is the material that we created. So, and click on, you could also preview it, and then when you click on preview, this is what you have, and then click on OK. Yes, so we have the first part. Now we go again to the brick and escape, and now I want to model this other part of the geometry. So we have that let's look at the y dimension. So the y maximum would be 4 centimeters, because from this line, your axis line to the maximum point is 4. So the coordinate is 4. So your y max is 4, and then the minimum point is -2, which is this point. So this is -2 on the y, and then your x is The minimum x going from left to right is this should be total is 5 cm and this is 2 cm, so this should be 3. So x minimum is 3 and x maximum is 5. And then z minimum and z maximum remains the same, minus 1 and 1. Then ensure that the material you created, which is material 1. Then when you click on it, you see that it brings this part. Now one thing we could do is we could create another brick and try to get the dimensions of this, but then an easier way would just be to mirror it. So I would go to modeling and then I would expand components, and this is a solid we just created and I want to mirror it, and I want to mirror it over the x-axis. So along, not over, along the x-axis. So solid 2, and then go to transform, click on the drop down, then mirror. So I want to mirror along the x-axis. So preview, and then this is what I have, and then I can click on copy. If you don't copy, then it only mirrors it, but then I want to make a copy of it, so I want to mirror and make a copy. So I click on copy, and then I could either click on apply or OK. I click on OK. So now I have 3 components. Now to make the components, I think it's here, yes, to make the components become just one solid component, I would use a boolean. So add in all of the shapes. So I go to boolean, I could click on the drop down and then click on add, then it makes all the solids just one solid. So I have the bottom part of the model. Now for the top part of the model, no, sorry, that's not it. Slide 5. Yes, this should be it. Yes, to create a fourth brick, I'm going to expand this a bit. To create a fourth brick, click on brick, escape, and then just copy these dimensions. This is easy. And y mean 4 plus gap, and this is 4 plus gap plus 2, and this is minus 1. This is 1. Now if you notice, I haven't created a parameter called gap. Now I could cancel out of this box and go here and create the parameter. I could already create it here, but then instead of going through that stress, I could click on preview, and then since there's no parameter as gap, it tells me that I should define the missing parameter. So I could also as well just click preview and then enter the value here. I think we missed that in the previous slide. No, we didn't. Gap is 0.3. I think you can see it here. Gap is 0.3 centimeters, so the value is 0.3. And then when I click on OK, it adds it to my parameter list. So that's another way you could add new parameters. So okay, we have our model. Now to define the current source, so we have to define the curves and then the part for the coil. So we have to define 2 curves. Now we just follow this. Okay, sorry about the break, I had to check something. Okay, so to define the coil, we have to define the path and also the profile. So for that we go to curves, so modeling, and then under curves you click on rectangle and escape, then you copy the dimensions here. So minus 1.2, 1.2, minus 4.2, minus 1.8, and I would rename the curve to path. That's this, and then I think everything should be okay. You could also preview it. So this is what you have. And then okay, so we have the path. Now we need the profile to loop, and it's also, you go to curves and then rectangle and escape. So you copy the dimensions, minus 0.5, 0.5, minus 1.9. minus 1.7, and then add it to a different curve. So new curve, and then rename it to profile. You could also preview, and then you see. Now, I think does it match? Yes, okay. Now we have to rotate the path by 90 degrees around the y-axis. So you click on the path and then transform. So you go to transform and then rotate, and then want to rotate 90 degrees about the y-axis. So we click on, we change it to 90 from 0 degrees, and then you could preview it and to ensure that here the rotation is correct, and then okay. So now we have our profile and also our path. So now what we have to do is we go to, okay, let me change this so you see it also. Now we go to, okay, we already did this. This is what I just did. This is click on okay, this is different. So go to simulation tab, click on coil, click on coil, and then select the curves profile. So you can also see it here, double click to select the profile. Now you select the profile, and then now the coil profile, wait, that's this one, and then enter. And now to select the path, so you double click to select the path and then press return, which is enter. And now you have the coil. Now the current of the coil is 1 ampere. I think I could also expand this so you see 1 ampere, and then the number of turns is 1000. You leave all other settings as they are, and then okay. Now we are ready to run our simulation. So let me go ahead and turn off the working plane. Yes. So this is our model. Our model is complete. Let's see. In the information, okay, yeah, we've already done that. Now add 5 cm to the background. Now I want to simulate this thing in normal background. So either from back modeling or simulation. So the background want to add 5 centimeters in all directions. So apply. Oh, okay. I could also view the bounding box. So this is the 5 cm we applied in all directions. Now click on magnetostatic solver and change the stopping criteria on the adaptive mesh to this. So simulation, magnetostatic setup solver. Now adaptive mesh refinement is on, and then we change this to 0.003, and okay. Now we could run the simulation by clicking on start. It shouldn't take long. So okay, and that's done. Now let's view the fields. Now observe the H and the B field in 2D 3D results. So when you go to 2D 3D results, you see the B field and the H field. But then like before, it shows the B field over the whole space. But we're actually interested in, or at least for this example, we want to see what goes on in a particular section of it. So we could look at the X section, or we could look at, I could change this to normal Z. Oh, why does this change? This is coming. Yes. Okay, doesn't change again. Now you could see the B field. and then the H field. You could see the B field and then the H field. So you could also scale it up or down. And that's it. And what else do we need to do? Now plot the H field in the indicated parts. So we have part 1, part 2, and part 3. So we go to post processing. Now, since we want to plot field results along a particular path, we select 2D, 3D field results. If it was not already selected, then we go to add new post processing step. Now, on this, we want to evaluate on arbitrary coordinates. Now, you could evaluate on arbitrary coordinates, or you could go to modeling and then draw a separate curve and then get the electric field distribution on the particular curve. But for this case, since it's a straight line, evaluate on arbitrary coordinates is sufficient. So we want to evaluate the H field along path 1. So we have to, so magnitude. Now path 1 is oriented along the y-axis. So direction y-axis. Now what is the x location of this path 1? We see that this is 5 cm and then this is 2. So we have that this should be at about 4, minus 4. So this is minus 4. And we want to get for z is equal to 0. So central value of z. So that's it. Hopefully I didn't miss anything. Now we just have to repeat exactly the same thing for the other one. So I've calculated for the H field. Now duplicate. I want to duplicate this for the B field. So it's H field currently. I would have to change it to B field because we want to get the field profile for both the B and the H field. So this is okay. So I'll just go ahead and name this part 1. And this is also part 1. And I could go to evaluate on arbitrary coordinates again. Then for part 2, that would be along the x-axis, so it's already there. Then 0 central z, and then what is the location of y? So we had initially that this is, let me go back, so this is 0, so this is minus 2, so this should be minus 3. Minus 3, and then okay. So I want this to be path 2, and then I just duplicate this for B. I have to change the name to B, and then part 2. Now I could also duplicate this for part 3. So H for part 3, and then settings, I change this to H field, and part 3 should be, this is 0, then this should be 4, and then at the middle of, maybe I should zoom this a bit. So this is at the middle of the gap, so the center of the gap. So this would be y should be 4 plus gap over 2, so half of the gap, and then okay, make this a bit smaller again. Now we have for the H field, and I just duplicate it one more time, and then for the B field, change it to the B. That's okay. Hopefully everything was done correctly. Part 3. Now I could sort this out, so I move this down. So I want to move all the B fields and all the H fields to be separate for easy selection. Now, yes, that's that. There's something I wanted to show. Have I forgotten? There's something I wanted to show, or maybe I'll remember again. So evaluate all of them. So that's done. Now we go to tables to see our results. So 1D results which we just evaluated. So H field, let's see for the 3. So for part 1, for part 2, and then for part 3, we see that the H field, this is the profile which is exactly the same thing we have in this figure. So maybe I'll make this a bit big. So this is the same thing we have in this figure now. The question says where is the maximum B field located, and where is the maximum H field located. So you could, from each of the plots, locate where you have the maximum B field and also the maximum H field. So for part 3, you have the maximum B field at about 4 cm. So that should be around. So for part 3, where is part 3? Oh, I covered it. So for part 3, you have the maximum B field along at this point and this point, so at the middle of the gap along the x-axis. Then for part 2, you have the maximum. Part 2 is the green one. You have the maximum at -5, which is at the edge. Is that correct? Yes, minus 5. Yes, just at the edge of the geometry. So at the edge, at the opposite edge of the geometry, because the length of this is 10. So you have from -5 to -5. So you have that, you have a jump in the magnetic field changing medium, because from this point is the material we define. Maybe I could zoom that also. With permeability of 1,000, and then this is kind of the interval, the boundary between the um, space, the normal space, and the material. So you have that, you have this is the H field jumping to the maximum value just at the region between the boundary between the normal space and the magnetic material, the material we define. So I could reset the view. And then lastly, we look at for part 1. So for part 1, we have that the maximum is around minus yeah, also this is -4. So at the edge, so also at the interval between your normal space and the not interval, the boundary between your normal, the interface. Yes, the interface, I got it. The interface between your normal your background material, which is normal, and then the magnetic material that we defined. So then you could also observe the profile for the B field and see the maximum and what happens at the interface between the two materials. So yes, that's that. And then calculate the force applied to the bar using this. Now, first of all, I don't quite understand what this question requires, and secondly, I do not know how to do this in CST Studio, so I'll skip it. And then find the appropriate symmetric boundary conditions to reduce the computational size. Now, like in the previous tutorials, you have to, first of all, you look at the geometric symmetry, and then you look at the field symmetry. So first of all, if we wanted to look at the geometric symmetry, we have that if we should draw a line, if we should draw a line like this, it will divide this into two identical parts. And then if we should look at this also, if we should slice it this way, then it divides it into two identical parts. But then what we can't do is we don't have a symmetry line along the x-axis, because if we should divide it, then we have different geometries at the top and the bottom. So that is for the geometric. So for your geometric symmetry is along the, let's see, this is the YZ plane, and also let's see, the YZ plane and the XY plane. Yes, the XY plane, which cuts this into, let's see, simulation or 2D 3D results sectional view. Yes. So you have, I think I should go ahead and turn off the bounding box. Yes. So you have a symmetry along this plane, and then you have a symmetry along the, let's see this, turn off one of them, and also along this plane. So you have a symmetry. Now you just have to go ahead and look at the, observe the field profiles. Now of course you can see here that you have just normal components. So your H field is normal to this plane, which means your tangential component is 0, so ht is equal to 0. So you could look at that and then look at the previous examples and apply the proper symmetry boundary conditions. So I'll leave that as an exercise. One way to check your answer is to see the results before you apply the symmetry boundary conditions, and after they should be exactly the same. And then run the, change the mesh to hexahedral mesh and view the mesh. So to change the mesh, I think I mentioned this in the previous tutorial, you go to global properties, and then you see you have planar mesh, you have hexahedral mesh, and you have tetrahedral. What we've been using so far has been tetrahedral, but then you could also change it to hexahedral mesh. Okay, I'll change it and then update it. So it will delete my previous result. And I do not want any sectional view. So I go to mesh view, and yes, so this is what I have. So you could also view the mesh along the y, no, not yz. So this is what we have from the mesh view. So this for hexahedral mesh. If I should change it to tetrahedral mesh, then we could also view that. Okay, then mesh view and update. So this is your tetrahedral mesh. So you see it's different. Now you run the simulation and then compare the number of mesh cells over time and accuracy. We've done this in previous tutorials, so I would not go over it again now. Now what we have learned, or what hopefully you have learned, how to use the magnetostatic solver, how to build a current coil, how to build a new material, how to inspect the field along a particular path, and the behavior of normal components at boundary between two materials, so the interface between two materials. So I hope you were able to learn all of this. You could, of course, go over the tutorial as many times as you want. So I think, yes, that's that. And see you next time.